So in this video, we are going to walk through the IR and the interpretation of IR. So so I'm sorry to inform you that the directory structure is changed a little bit. So now in SRC folder, there are multiple folders, and the IR is in this IR folder. And also the writec.rs, which is the homework you're going to implement, is in the C directory instead of the SRC directory. So please change your please download the update in the upstream repository and merge it and work on your homework in this directory. So your file, you can just paste your file into this directory and then work on the homework. So today we're going to look into this IR directory. So let's go to the mod.rs, and it defines the abstract syntax tree of the IR, or syntax of IR, and the interp file is defining the semantics of IR. So these two files are the syntax and semantics of this IR. So at the beginning, an IR program is this translation unit, which is a map from string to a declaration. So let's think of this kind of example like this. I mean, if a C file is consisting of multiple functions and, for example, declaration, then each of them is a declaration in each of them is going to be translated into a declaration here. So the string is the name of the variable. So a main foo, for example. So decals is basically a map from string to a declaration. A declaration is either a variable or a function, and a variable has a type. So it has a type of its variable, and furthermore, it has an initializer. If in this declaration, int will be the data type, and this 42 will be initializer of this variable. On the other end, a function is consisting of a signature and its function definition, and the signature here can be like this. This is the function that is returning void, and this is the function signature of this function foo. And the definition here is going to be this part. So this will be stored in this definition. But it is optional because in C program, you may have a declaration, function declaration, instead of function definition. So in that case, we are not going to have a body as a definition. We will just have none. If it is defined, the function is defined and it has a body in the C program, then it will have some function definition. Okay, so this type, we are going to discuss this type in another file, which is in ir_dtype.rs, and it defines the data type, which is either unit, which is the another name of void. Basically, unit is void, and integer and float and point and function. And we are going to introduce array and structure in the future. So we are going to upload the revised IR, so please download whenever we upload further updates. So we are going to add array and struct in the future. So let's look into this file later, and let's go back to the mod.rs. So we are going to define functions for this declaration. So one function, such a function is try from dtype. So we are going to define a declaration from a D type. So this is the purpose of this function. So for example, if the type is void or unit, then it is an error because you cannot declare a variable of type void. But if it is a type integer, float, or pointer, we are going to have a declaration. And furthermore, if the type is function, we are going to have a declaration of a function instead of this variable. So we are going to divide the cases for non-function types and function types here. And there are a bunch of helper functions. For example, it is given a declaration, a reference to declaration, and it is giving you either some content of the variable or not. If it's a variable, it is returning to the references to the internal data, or otherwise, if it's a function, then it is going to return nothing. Similarly, you're going to have a helper function for getting the internal data of function, and mutably also, and things. Okay, so these are the internal functions of these declarations, and we're going to have a very handy helper function as well. So every declaration has a D type. So if it is a variable, it already is annotated with D type, so you're going to return it. And if it is a function, the function signature decides its function's D type. So we're going to return the signature's D type in here. So overall, this means that the implementation of this function means that every declaration has a D type. For another example, let's look at the function signature type, which is just consisting of the type of return value and type of parameters, and it can be constructed by given D type, and it's going to look into the internal return and parameter types of function types and construct the function signature. And it is also we can also reconstruct D type from a function signature by returning a function type that is consisting of return value types and the parameter types. So this is the D type of function signature. Okay. So this is the declarations helper functions. And let's move on to the function definition. A function is consisting of three data, which is the number of a number of allocations, local variable allocations, and the basic blocks and the initial blocks ID. So this is related to the CFG or control flow graph we discussed in the previous video. So instead of statements, blocks are comprising the IR's program. For example, this if statement, if condition, then A or else it is B. This is translated into such a form. So there is a block that is calculating count, and depending on the value of this condition, it is going to go to the block that is consisting of A. And if the condition is false, it is going to jump to B. And at the end of the both blocks, it is going to jump to the continuation block. So it can be consisting of count A, B, and count block, and it is flowing through. It is flowing the execution through the basic blocks. So it is so this blocks is defining such blocks, and this is defining the initial block of a function. When your function is called, then you're going to begin with in the initial block stated here. So that is basically the meaning of this three data. So regarding these allocations, we probably need a little bit more explanation. Let's say that a function foo is having a local variables here. Then it is going to be allocated at the beginning of a function in our IR. So this has the list of such allocations as their types. So for example, if it declares two local variables, then in the translated IR, allocations has two elements that are int. So we are having two allocations here and here, and each of them have the type int. So this is basically the meaning of these allocations. Okay. So we already looked into function signature and its associated methods, and this is basically so far we basically defined the high-level structure of the IR. The translation unit, which is the whole program, is consisting of multiple declarations, and a declaration is either a variable or a function, and a function has an internal body that is consisting of the list of allocations and the control flow graph. And now we are going to discuss how each of these blocks is consisting of. A block is consisting of, where's the block? Oh, here. Three things. But for now, let's ignore these finals. It will be discussed in later when we are going to discuss the mem2 reg. So let's think of it as an argument of a basic block. So if a block A jumps to a block B, in general, you can have variables here. So at the end of the block A, we are going to say, oh, I'm going to jump to B with some variable, register 1 and register 2. And at the beginning of this block B, it can say that I am accepting two values, and I'm going to assign them into register 4 and register 3 and register 4. And then the semantics here is that the value of R1 and R2 are copied into the registers R3 and R4. So these finals are defining such a parameter here in the viewpoint of this B, the block you're going to jump to. You're going to define the number of registers here with the types. So this R3, for example, this R3 has an int. This R4 is float. Then the finals of this block is going to have a list of two elements, and the first element is int, and the second element is float. So we are going to revisit this topic when we see the interpreter of this IR. Okay, so finals are such a thing, and instructions is that so a block A is consisting of multiple instructions basically. So for example, it is going to assign, uh, I mean, it can first calculate the addition of two registers and assign it to another register, and maybe it can do some other kind of operations, and maybe it can call a function foo with an argument given here, and blah blah blah. So each of these line is an instruction. So it is stored in a block as a vector of instruction or a list of instruction. And now at the end of it, a block, it is describing what it is going to do after finishing executing the instructions. So at the end of a block, it is written, for example, oh, I'm going to jump to block B, or I'm going to conditionally jump depending on the value of register. And if it is true, I'm going to jump to the block C. And if it is false, I'm going to jump to block D, etc., etc. And or maybe I can return this function. So I'm executing this block in a function, right? So I'm going to return this function with a return value R20, or even we can return 42. So this is defined here, a block exit, which is describing the behavior it is going to do at the end of a block. It is exiting the block with this behavior. So let's look at this instruction first. Then block is consisting of the finals, like the argument of the block, and the instructions, and the exit, and yeah. So let's look into a little bit deeper about this jump. Actually, it is going to give an argument here. So every jump should have an argument. And for example, we're going to jump to B with arguments, this R1 and R2. So this is basically describing the behavior written here. Let's write here. So A is jumping to B, but it is going to give this as an argument to the next block, which is B. And this is stored in, this is written to these registers. So this argument from A is written here. I'm going to jump to B with the argument like this. And these parameters are described in the finals. So this describes the argument of the jump, and this describes the parameter of the jump. So, and it is going to be dealt with in the interpreter. Okay, now let's turn to the instruction. An instruction is either binary operator, unary operator, store to the memory, load from memory, calling a function, or typecast, and blah blah. So, in fact, we are going to add a few more instructions in order to deal with array and structure. So, but for now, let's look into these 6 instructions. So, for example, a binary operator is given a binary operator, basically. I mean, binary operation has a binary operator. So, for example, if we have this instruction, this plus is the binary operator. Oh, I have a plus. And this R2 is LHS, and this R3 is RHS. And this D type is going to describe the type of the result. So this is annotated with the result of this instruction. But now you can see that RHS have a type of operand. And what is operand? Operand is either constant or a register ID. So actually you can do addition between a register and a constant, for example, because both of them can be an operand. So operand is either constant, for example, 42, and register, for example, plus percent ampersand R2. So going back to the binary operator, you may notice that it doesn't describe the name of this target register. So you're going to add this too with this type, but you didn't describe the name of this register that you are going to write to. This is in our IR. This is canonically decided by the position in the block. So let's look at the definition of this register ID. So this is going to be the register of the target register of each instruction. So for example, this is consisting of a block ID and instructions ID. So if you have a block like A, then the first register is named like this. A's and zeros temporary variable. I mean temporary register. That is, for example, another register that is, for example, R's 3 register plus 42. And the second register is canonically named as A clone 1, where this BID is A and IID is 1. So this is the index 1 register inside this block A. This can be A0 times 2 and blah blah blah. So all the registers are canonically named. So we don't have a freedom to choose a register name for this. So in the future, maybe it is beneficial to name them explicitly in order for the readability. But for our purposes, let's just say that its temporary register has this kind of very strict naming principle. So that's the reason why this instruction bin up doesn't have the target register, because it is canonically decided depending on the position of this instruction inside a block. If this is the first instruction, zeroth instruction inside the block, then it is going to name like this. Or if it is here, then it is going to be named like this, and blah blah blah. Okay, we also have a unary operator, which is very similar to the binary operator. And we're going to have a store instruction that is given a pointer and a value. And this is going to be calculated into a pointer. And this store instruction is instructing us to write the value of this after calculated should be stored into this pointer. And this is the load, and this is a call. So this is the function pointer of the callee. If it is going to call a foo, then the function pointer of foo is given here. And it is going to be the argument. It is going to be the list of arguments. And each of the arguments can be either constant or register. And it is going to have a return type of this, explicitly annotated in order to ease the job of type checker, basically. So it can be decided when you look up the callee, because callee has a function signature, which in turn has a return type inside it. But we don't want to look up the function just in order to know the return type of this. So that's the reason why we are writing down the return type here. Similarly, we have a typecast. If you are casting integer of 32 bits into integers of 64 bits, then you're going to use such an instruction, typecast instruction. And this instruction has a bunch of the associated methods. For example, it is going to return the data type of each instruction. I mean, the result of this instruction, basically. For example, and we have a definition of this block ID, which is just a number, and we are going to, yeah, that's basically the end of the explanation about the instructions. Now let's go back to the block. It has instructions and block exit, and here is the definition of block exit, which is either jump, conditional jump, or switch, that is jumping to different blocks based on the value of this operand. So this is intended to be the target of the switch instruction in C. Like this. And this is returning the value, and unreachable is a special block exit, that is meaning that, oh, you cannot reach here. If you reach here, then it is very wrong about your program. So interpreter will immediately stop and report that, oh, I just exited with an unreachable block exit, and it is very bad, and you're going to debug your program. And each jump, here and here and here, it has jump argument that is basically describing the jump target. For example, I'm going to jump to block B, and in addition, it has an argument of the jump. So as we discussed in this example, every jump has an argument. It can be multiple operands, and this jump argument has this argument in this args variable. So these jumps and conditional jumps and everything have jump arguments, and it is consisting of the block you're going to jump to and the argument of the jump that will be stored in the finals. Okay, so that is pretty much everything about the IR in this KCC compiler. So in the next video, we are going to look into this interpreter, how this ASC or syntax is executed, what is its semantics. So we are going to describe it in the next video.